we had finished our discussion on nuclear fission reactions. We have seen that this is an important reaction because it produces energy, and lots of our energy requirements do come from fission reactions. Next session that I am going to start is on nuclear fusion reactions. So, let us start with this new chapter. This is nuclear fusion reactions. This chapter is also very important, again from applications point of view, and same applications. Nuclear fission is used for energy production, electricity production. Nuclear fusion can also be and is used for energy production. In fact, everyone knows, it is a general knowledge, school students also know, children also know, that the energy that we get from sun comes from nuclear fusions going on inside the core of the sun, and only because of that energy all life and everything is there on this earth. And we are also trying to produce nuclear fusion reactors where energy can be produced, electricity can be produced from nuclear fusion reactions. So, let us first revise the basics of this fusion reaction. In fission, a nucleus splits in two parts, and then if the nucleus is quite heavy, the Q value is positive and energy is released. In fusion, two light nuclei fuse or combine to form a bigger nucleus, and from that also, if the nuclei are small enough, energy is produced, Q value is positive. So, if you remember that binding energy per nucleon versus nucleon number, mass number curve, if this is the mass number of a particular nucleus and then the binding energy divided by this A, binding energy per nucleon is here, on the average it increases in the beginning and then it goes to a maximum and then slowly decreases. This is the kind, and this maximum occurs somewhere around this 56, 57, that is iron, nickel, that region. It does not go this smoothly, as you know very much. Different nuclei will have different fluctuations around this, but this is the general average behavior of this binding energy per nucleon versus A. We have used it several times by now. In fission, the original nucleus, the parent nucleus is a heavy nucleus, and the binding energy per nucleon is small. If I shift it this side, if it splits in two parts and you have two nuclei in this region, the total binding energy per nucleon increases, and as the binding energy per nucleon increases from here to here, you get this energy released. Now, the other side of this maxima here, if we start with two nuclei somewhere here in this region, the two nuclei are around this, maybe two nucleus I can show slightly different. It can be two nuclei of the same species or it can be two nuclei of different species, but the binding energy per nucleon is in this region this much, whereas if they combine, they will go somewhere here, and then the binding energy per nucleon will be here. So, if the binding energy per nucleon is more, the nucleus is more tightly bound, then the rest mass energy decreases and you get kinetic energy, and that is the energy released. So, from this side also you can get energy, from this side also you can get energy. If you get from this side, that is nuclear fission, and if you get this from this side, it is nuclear fusion. So, the reaction would look like some X and some Y, some light nuclei going to a heavier Z, and probably some small particle like neutron or gamma ray, gamma photon, or say neutron or some such light particle may also be there, or maybe two particles, but most of the nucleons which are here in this X and Y, most of them are here in this bigger nucleus Z. We can take some example. Let us take, for example, 20 neon. 20 neon, neon Z is 10 and neutron number is also 10, total is 20. Suppose 20 neon and 20 neon, that goes to 40 calcium, right, plus of course gamma or something. So, if I look at the Q value, how much is the rest mass energy on the left, how much is the rest mass energy on the right. So, if I look at this rest mass energy at the left, it will be mass of this 20 Ne C square. This will be, you have 10 protons. So, 10 MP plus 10 Mn, this is proton mass and neutron mass. So, these are the masses of these nucleons separately times C square and minus binding energy. How much is that? Minus binding energy is minus 20 times Be by A at 20. Understand the symbols? Here I have to write the binding energy. How many nucleons are there? Total nucleons here is 20. 20 neon. I am writing mass of 20 neon nucleus times C square. So, 10 protons, so 10 proton mass, 10 neutrons, so 10 neutron mass, rest mass of that, minus binding energy. How much is binding energy? Binding energy per nucleon multiplied by total number of nucleon. Total number of nucleon is 20, so this 20 is here, and binding energy per nucleon is here Be by A, binding energy per nucleon, where, because binding energy per nucleon is this curve. So, where? Here 20, A equal to 20, at A equal to 20, so that is this 20. And two of them, if I calculate the total rest mass energy on the left, two of them, so it will be before fusion. Before fusion reaction will be double of that. Double of that will be say 20 MP plus 20 Mn times C square and minus 40 times Be by binding energy per nucleon. So, Be by A at 20, at A equal to 20. That is the rest mass energy before the fusion reaction. What happens after fusion reaction? After fusion reaction, you have a single nucleus calcium 40. So, you have this calcium 40, Z is 20 here. So, rest mass energy of this, so that will be now rest mass energy, same expression, rest mass energy after this fusion reaction. This will be, you have 20 protons and 20 neutrons. So, the rest mass energy of this mass of 40 calcium times C square, this will be 20 mass of proton plus 20 mass of neutrons times C square, that is the rest mass energies of these nucleons if they are widely separated from each other, but they are not, they are all bound in this calcium nucleus, therefore minus binding energy, and that binding energy will be 40 times binding energy per nucleon at A equal to 40, because now you have a nucleus with A equal to 40. So, the binding energy per nucleon is given by this binding energy per nucleon at A equal to 40 in this binding energy curve, wherever that 40 occurs. So, binding energy per nucleon at A equal to 40 multiplied by 40, because there are 40 nucleons in this. So, what is the Q value? Q value is the initial rest mass energy, the rest mass energy before the nuclear reaction, and minus the rest mass energy after the nuclear reaction. So, Q value is how much is the rest mass reduced because of this reaction. So, Q value is this minus this. So, 2 times mass of neon C square. This is the rest mass energy before the reaction, and from this we will subtract this mass here. So, this will be mass of 40 calcium into C square. And when you do that, when you subtract this final mass from this initial mass, all this 20 MP plus 20 Mn C square cancels out, this cancels out, and here you will have this minus this. So, this will become positive. So, this is equal to 40 times Be per nucleon at A equal to 40, right. You are subtracting the final rest mass energy from the initial rest mass energy. So, this becomes plus 40 this, and here it is minus 40 times Be by A at A equal to 20. So, 40 also you can take common, and 40 multiplied by, this is 40 multiplied by binding energy per nucleon at A equal to 40 and minus binding energy per nucleon at A equal to 20. And since binding energy per nucleon at A equal to 40, suppose this is 40 and this is 20, then at A equal to 40 is larger and binding energy per nucleon at A equal to 20 is smaller. So, this difference multiplied by 40 positive, and this turns out to be about 23 MeV in this case, mega electron volts. If these two neon nuclei, they combine and fuse to become one single calcium nucleus, the rest mass energy is decreased by 23 MeV. And if rest mass energy is decreased by 23 MeV, that should appear as something. So, in this case it can appear in excitation of this calcium and subsequent emission of gamma photon and recoil of calcium. So, this is an example. Whenever you combine these nucleons in this zone, light nuclei zone, and make a nucleus which is somewhat heavier than that, but do not cross this peak, you will get Q value positive. So, this mode of energy production from nuclear reactions using light nuclei and their fusion has several advantages over what we are currently using, that is nuclear fission reactions. We had discussed all the radioactivity problems, accident problems, hazards, then availability of nuclear fission fuel. So, those problems will be much lower, much lesser if one can use these fusion reactions to produce energy. So, that is one motivation for understanding these nuclear fusion reactions. Another motivation is that if we want to understand what is going on in stars, what is going on in sun, how all these different elements, nuclei of different elements were created for the first time, astrophysics, little bit of astrophysics. So, there also nuclear fusion is the central phenomena, and therefore, understanding, knowing these fusion reactions, physics of it will help us in understanding all those astrophysics problem also. So, all these things we will briefly discuss in this section. Now, it looks very simple, just take two nuclei or two species of nuclei with smaller mass numbers, light nuclei, and put them together to fuse, and you get energy. But it is not really that simple. Nuclear fusion reactors are still not commercially made. People are working very hard for decades and decades, and we are only hoping that we will get this nuclear fusion reactors in near future. So, what is the problem? The problem with it is that Coulomb barrier. We had talked about Coulomb barrier during alpha decay discussions. We have talked about Coulomb barrier during fission reactions, and once again this Coulomb barrier comes because you are working with positively charged particles. The nuclei which are combining, they are all positively charged. So, initially you have two different nuclei. So, they are apart from each other, no new nuclear reactions, it is interacting through Coulomb force only, and therefore, the potential energy will be given by that usual Z1 Z2 E square by 4 pi epsilon naught r. So, if I plot that, energy this side and the separation between the nuclei this side. So, if you have two nuclei which are approaching each other and finally, they are trying to combine. So, this separation r is what we are plotting on this horizontal side, and then the energy is on this side. So, initial energy, if they are widely separated, if this r is much larger, that if I take as 0. So, you have to take care of rest mass energy also. So, when they combine and form one big nucleus, when they combine and form one big nucleus, that means now r is very small in the nuclear range, the rest mass energy has gone down, and therefore, you have to, the energy will come somewhere here if I take this as 0. So, as compared to the rest mass energy of this, rest mass energy of this is down. So, that is the Q value, and from here if this r decreases, if when they come closer and closer, this Coulomb potential energy V Coulomb, that is Z1 Z2 E square by 4 pi epsilon naught r, this keeps increasing. As the particles come closer, r decreases and this V increases, just as hyperbolic 1 by r pattern. So, it goes like this. The usual Coulomb potential nature, and then when they come very close to each other, you can say when they are touching, they are going, now they are going inside, then the nuclear forces will take over and the potential energy will decrease, and that will finally come here. So, somewhere it goes back and comes like this. Now, what is the initial energy available? That is important. This height, first this height, how much is this height? How much is this height? So, if I just take the simplistic model as we had done earlier also, that when these two just touch each other, that time, till that time we say that it is only the Coulomb force which is effective, and once they have touched and now they are going into each other, that time we say that the nuclear thing has taken over. So, the maximum will correspond to this maximum, which is the barrier height, this V naught will be Z1 Z2 E square over 4 pi epsilon naught and R1 plus R2. radii of the two nuclei which are trying to combine. So, that is this situation R 1 and plus R 2, when r is small r is equal to R 1 plus R 2, that we take as the maximum potential energy here. So, that is the barrier height. We can estimate how much it is. Let us take again the same example for say 20 neon plus 20 neon. For this, if I make, so 10 Z 1 is 10, Z 2 is 10. So, it is 100, Z 1 Z 2 is 100. Then we have E square over 4 pi epsilon naught. We have used this several times. It is 1.44 MeV Fermi or MeV femtometer, and then divided by 2 times R 1 plus R 2, 2 times radius of this. Now, radius of this you can estimate, R is equal to, take 1.2 femtometer times a to the power 1 by 3. So, you can put a equal to 20 here, cube root of 20 will be little less than 3, cube root of 27 is 3. So, that multiplied by 1.2, so something like 3.5, 3.6 femtometers, and double of that will be 7.2. Let us take it 7.2 femtometers. So, how much is this? This will be almost 0.2 here, and so it will be 20 MeV. So, this height for this particular reaction is 20 MeV. For 20 neon plus 20 neon. This height will be large if Z 1 Z 2 is large, and it will be small if Z 1 Z 2 is small, and smallest value of Z 1 Z 2, how much that can be? That can be when Z 1 is 1, Z 2 is 1, so proton proton. In sun or in stars, when hydrogen fuses, the first step is proton proton. So, there the Coulomb barrier will be minimum Z 1 Z 2. So, if I take just that case, it is Z 1 Z 2 is 1, and for radius take 2 femtometer, the range of nuclear interactions, so 2 femtometer here. So, this will be 1.44. So, for proton proton, this V naught will be equal to Z 1 Z 2 is 1, and E square by 4 epsilon naught, that will be 1.44 MeV femtometer, and for this R to take 2 femtometers. So, that will be around 700 keV, 720 keV, kilo electron volts. So, for nuclear fusion, this will be the minimum barrier. Of course, if one can go for deuterons and tritons, higher isotopes of hydrogen, in which case Z 1 Z 2 will not change, you still have Z 1 is equal to 1, Z 2 equal to 1, and then the radius will increase if you go for higher isotopes. So, but still hundreds of keVs minimum. So, that is the kind of Coulomb barrier is there. Now, if the world were of classical physics nature, fusion would have be possible only if the initial kinetic energy of these two nuclei is more than this barrier. And in quantum mechanical world also, the probability increases as you go up, and if you can surmount that barrier, then the probability is very, very high. Now, in our case, if we want to compare the initial kinetic energies and this barrier height, we have to give at least hundreds of keVs minimum, and depending on what nuclei we are trying to fuse. If we are trying to fuse something like 20 plus 20 making it 40, remember 56 is our barrier, we should not cross that. So, if I use that 20 neon type reactions, then the energy needed, if I want to surmount that, not penetrate, surmount that, should be like 20 mega electron volts. Now, giving initial kinetic energy of 10 MeV, 20 MeV, 30, 40 MeV, 50 MeV is not a problem. We have nuclear accelerators. In nuclear accelerators, the ions, you can strip all the electrons and you can make this nucleus. So, that ion is accelerated, and 10-20 MeV is a small energy for most of the accelerators which are there. And one can have some kind of a target, and accelerated beam can hit and nuclear fusion can take place. This kind of reactions are done in research laboratories to understand the fusion mechanism of these nuclear species. But if you think of producing energy, if that Q value is in mind, if we are trying to get energy from that reduction in rest mass energy, this mode of providing initial kinetic energy to increase the barrier penetration probability to a very significant level, where the barrier height is comparable to the barrier height, is not feasible, because to maintain that accelerator, to maintain that machine, to run that machine, lot of electricity, lot of power will be needed, and the output that we are going to get from this is negligibly small as compared to what we give to run that accelerator. Another way to get this initial kinetic energy is through random thermal motion. If we think of any system, gas, the molecules or the particles are in random thermal motion and they have some kinetic energy. So, if we create some kind of plasma where the electrons, we take it to high, we take particular species and then we take it to high temperatures, so that the electrons are removed from the atoms and you get a plasma, and you have these nuclei and electrons of course, and depending on what the temperature is, they will have some kinetic energy. The nuclei and electrons, they will have some kinetic energies, they will be moving in random directions inside whatever volume you have provided, even in which that is confined. So, occasionally two nuclei will approach each other with certain kinetic energy, and that kinetic energy can be used to get some significant barrier penetration. When the fusion is, nuclear fusion is done using this thermal kinetic energy of the particles of these nuclei in a gaseous type of system confined into a volume, we call it thermonuclear fusion, right, thermonuclear fusion. So, thermo, that means we are using thermal kinetic energy, and of course, nuclear fusion. So, this is thermonuclear fusion. All the reactions that are going on in stars are essentially these thermonuclear fusion, because there no one has put any accelerator or any such thing. It is only because of the temperature, only because of the thermal kinetic energy that those fusions are taking place. And in nuclear reactors that are being planned or being investigated or being designed or being researched, that is all based on this thermonuclear fusion. So, let us see what kind of temperatures are needed if we have to get some significant barrier penetration probability, what kind of temperatures will be needed. So, let us look at that, and let us start with room temperature. So, at room temperature, that means 300 Kelvin, kT is 0.027 electron volts, not keV, not meV, electron volts, 0.027 7, that is Boltzmann constant K times the absolute temperature T, and the kinetic energy of the constituent particles at temperature T. Scale is decided by this K T. In a thermal system in equilibrium at certain temperature T, different particles will have different kinetic energies. There will be a distribution of energies among those particles, and you can take that distribution to be Maxwell Boltzmann distribution. But then what is the average? What is the most probable? So, all this is that scale is decided by K into T, 3 by 2 k T or 1.5 k T. That is the average kinetic energy, all those kinetic energies of different particles. If we average, that is 1.5 times k T. So, that is the scale of kinetic energy in thermal motion. So, at room temperature it is 0.027 eV. So, if I take this average 3 by 2 k T or so, this kinetic energy, this initial kinetic energy is hopelessly small when we compare to the barrier height. Even if I take say 300 keV of barrier, 300 keV kilo electron volts, that means 300,000 electron volts, and here it is hardly 0.03, 0.05 type of electron volts. So, the barrier penetration probability will be very small. If I want to have a comparable initial kinetic energy comparable to the barrier height, let us calculate what should be the temperature. So, let us take 3 by 2 k T as this is the average kinetic energy. So, let us say that let us take a temperature where it is 150 keV kilo electron volts, right. For proton it was 720 kilo electron volts of barrier, and if you go for slightly bigger like deuteron or triton or so on, that will be reduced little bit from 700 little bit because of that radius increasing, okay. But still it will be several hundreds of keV. So, let us say that our temperature should be such that the average kinetic energy is 150 keV. So, that when the particles come and try to combine, the kinetic energy is comparable to the barrier height, and then the barrier penetration probability is significant. So, how much is this temperature? This temperature will be T equal to, I have taken 150 for one more reason, this is 1.5. So, k T is just 100 keV. And this divided by Boltzmann constant, and Boltzmann constant you can write 8.6 into 10 to the power minus 5 eV per Kelvin, right. That is one unit is in terms of joules and so on, but this is also in terms of electron volt, this is the value. So, how much is this? How much is this? This is kilo electron volt. So, 10 to the power 3 will come from there, 10 to the power 5 here, and 10 to the power 5 from here. So, this will be 10 to the power 10 and divided by 8.6. So, something like 10 to the power 9 Kelvin, 10 to the power 9 Kelvin. This is a very high temperature. The temperature at the core of the sun is around 1.5 into 10 to the power 7 Kelvin. So, 2 orders of magnitude less. Temperature at the core of the sun is 1.5 into 10 to the power 7 Kelvin, and if you look at that k T 3 by 2 k T, it will be around 1 kilo electron volt. So, compared to 720 kilo electron volts of Coulomb barrier, the kinetic energy of these protons which are coming will be around 1 or 2 kilo electron volts, very very small, but still sun is able to produce so many fusion reactions, so many protons are combining and giving all this energy. That is because the density is very high, that is because of the enormous density there. The pressure of hydrogen there is something like 200 billion times our atmospheric pressure. The density is some 160 times the density of water, the density of gas there in the sun, the density of hydrogen there in the sun in the core region is some 160 times the density of water what we have here. So, because of those high concentrations you have reasonably good amount of fusion taking place and energy coming out, but whatever the temperature has to be very high, 10 to the power 7, 10 to the power 8 of that range to get a reasonable barrier penetration. So, apart from this high concentration of the constituent nuclei, that is protons inside the sun, another thing which helps is that Maxwellian tail of the distribution. The average kinetic energy 3 by 2 kT, that is around 1 kilo electron volt. So, that we discussed, and that we are comparing with this barrier height of 700 kilo electron volts. So, that is very small, fine, but then this 1 keV is only the average kinetic energy of those protons. But there are protons which will be having kinetic energies 10 times this, 20 times this, 25 times this. There will be some protons. So, that is the Maxwellian tail on the higher kinetic energy side. If you look at that Maxwell Boltzmann distribution, that means if you have a gas, normal gas, let us take normal gas which has molecules. So, if there is the temperature is capital T, then how many of these molecules are moving with speed say some v to v plus dv. So, that number we write as NV, NV dV, number of molecules moving with speed between v and v plus dv. So, the expression for this NV is some constants, if I remember, 2 by pi to the power half and then m by kT to the power 3 by 2, and then you have v square e to the power minus half m v square by kT, and this is actually out of the total. And if you make a sketch of this, how does it look like against V? Against V, if you plot this NV, that will reach some maximum and then will decay because of that exponential minus half mv square by kT factor will go like this. So, here you have maximum number of molecules at this speed. The average will be also around this region, that 3 by 2 kT will be around this region, little bit shifted from here. But then you also have molecules with this velocity, which is much higher than the average speed. You also have molecules with this speed, which is even higher than the average speed. You also have molecules and so on. So, you have molecules with kinetic energy. Of course, that fraction will keep on decreasing. most of the molecules are here, largest number of molecules are having this velocity or close to this velocity. But so, the number will keep on decreasing as you go for higher and higher speeds, but still there will be some. So, if the densities are high, you have a significant number which are having much larger kinetic energy than that average 3/2 kT. And for those, same happens with this nuclei as a part of plasma at those high temperatures. Of course, at these high temperatures 10⁻⁷ and 10⁻⁸, nothing will be in molecular form and or atomic form. It will all form a plasma there. You have nuclei, you have electrons and so on. So, those nuclei which are moving towards each other with kinetic energies larger than 3/2 kT, they will have higher barrier penetration probability. Barrier penetration probability, if you remember, if you have a barrier and this is, let us say, R1 and R2, this is R1, this is R2, this is VR, here is VR, and this is energy, this is energy available, this is energy available this much, and this is the barrier, and one has to go from one side of the barrier to the other side of the barrier, tunnel through this. How much is the probability? How do I get that? That probability, especially if this energy is much smaller than the barrier height, not like the figure I have drawn. Assume the thermonuclear fusion, for example, that case this available energy is always very small as compared to the total height here. So, in that approximation, when the barrier height is too big, this probability is e to the power minus 2 integration gamma r dr from R1 to R2. And what is this gamma r? This gamma r is square root of 2 m by h cross square v at r and minus e, this is gamma r. So, v r minus e. So, at this r, for example, it is this one, this is v at r, this is v, this function is for the potential energy, this is v at r and minus e. So, this much, and this into dr. So, this into this 2 m by h cross square, of course, square root and all that, and then dr, and this you integrate from here to here to get that probability. So, as the energy goes up, this probability increases. So, if on the same scale, if I try to plot that barrier penetration probability, probably we will not be able to show it here. This in fact falls very sharply. So, at the scale of drawing, it will fall to almost 0, you will not be able to distinguish, and the barrier penetration probability, that will go, let us say, when you have very small velocities, the particles are going with very small velocities, almost 0, you are not able to see, almost 0, increasing, but still at this scale it is almost 0, and then probability will start showing up little bit and it will increase. So, in these regions the barrier penetration probability is negligible, almost 0. So, you have lot of particles colliding with each other, but they are not able to penetrate the barrier, and here when the barrier penetration probability becomes somewhat significant, the number goes down, but still there is some overlap region where there are some nuclei with certain energies, and here there is some barrier penetration probability also. So, at the end of it you get some fusion reactions. So, that is how it goes. Now, this rate of reactions, how many fusion reactions will take place per unit time, that is an important parameter. Nuclear astrophysics, or it is our fusion reactors, the in making, whatever, this reaction rate, how many fusion reactions will occur or are occurring in a given condition. Conditions means what are the conditions, what will decide this nuclear reaction rate. The parameters will be first concentration, how many these constituent nuclei are there. If it is x plus y, reaction x plus y, how much is the concentration of x, how much is the concentration of y, per unit volume how many nuclei are there of x, of y. If it is same x plus x going to a bigger nucleus, then concentration of x. So, that is one parameter. Other parameter is the temperature. So, depending on what temperature it is, the reaction rate will be decided. So, in a given volume with a given concentration of these constituent, how much is the total output, how much is the total number of fusion, and from each fusion of course, we know how much energy will be obtained. So, that is reaction rate. So, that is an important parameter, and our next task will be to talk about these reaction rates. So, given volume, given mass or number of reacting nuclei and temperature. How many fusion reactions take place or will take place per unit time. So, it will be first it will be proportional to the concentrations, that is almost obvious, understandable. If you have more concentration of the two, if it is different species x plus y and you put large concentration of x and small concentration of y, then also it will not help. So, the product of concentrations. So, that is quite obvious. Then it should be proportional to the cross section for this fusion reaction. Now, cross section itself is defined in such a way that the probability, if the two nuclei are approaching each other, and for that particular pair, how much is the probability that they will go for this reaction. So, that probability is directly related to the cross section. So, that cross section, it should be proportional to the cross section. Another thing which it is proportional to is the relative velocity of these two. So, this reaction rate r, this is not radius of the nucleus, we are using the same symbol for that also. It is the reaction rate that we are talking of. This reaction rate will be proportional to some constant Nx concentration of x, Ny concentration of y, sigma times V. I will justify why it is proportional to V, sigma times V. V is the relative velocity of these two nuclei which are approaching each other for fusion. But then as I said, all these pairs or all these nuclei which are moving in this thermonuclear reaction volume, they are not going with the same velocity, the Maxwellian distribution. You have some particles going with this velocity, some particles going with that velocity and so on, and therefore, one has to take average of this whole reaction rate that we are writing for a particular V. If we consider a particular velocity, relative velocity of a pair, then it is this. And if it is since it is all distributed, it has to be an average, but not average of this velocity, because the velocity also comes into this sigma. This sigma also depends on velocity, that also I will justify. So, it is average of this quantity that comes in for reaction rate. Okay. So, this expression I will justify or talk more about it in the next lecture, how this sigma depends on V and how this is calculated and those things, the reaction rate and this, all these things we will discuss in the next lecture.